Hello, welcome back to the lecture series in wave optics. In last few lectures, we have discussed about the Fraunhoffer diffraction at a single slit. We have discussed how the interference pattern form, how the central maxima, what are the conditions to form the central maxima, how the minimas and what are the conditions for the secondary minimas and the secondary maximas. Now, in this lecture we will discuss the Fraunhoffer diffraction at a double slit. Instead of a single slit, we will be using two slit in this particular case. In this case, we are assuming a plain monochromatic wavefront is incidenting on a two slit arrangement. Here one slit and here it is another slit. Now, the light is spreading through these two slits and it is showing a beautiful image of the diffraction pattern formed here. And how the diffraction pattern formed, where the maxima will be formed, where the minima and secondary minima will be forming, secondary maxima will be forming. So, this will be the point of discussion in this session. Yeah, this is a pictorial representation of the double slit diffraction experiment. Here obviously we have a source of light and the source of light is essentially a rectangular slit, and that slit is perpendicular to the plane of board in the direction of this pen. Then obviously this will be sending out the cylindrical type of wavefront. Now, that cylindrical wavefront is passing through this lens and the lens will make that cylindrical wavefront into a plane wavefront. Now, the plane wavefront is incidenting on the slit S1 and S2, therefore, this becomes a Fraunhoffer type diffraction. Two slit, one is the S1 and the slit width we take it as E. E is the slit width and S2 is a similar slit with the same width we are considering here. So, E is the width of these two slit and we can take D as the distance between these two slit, that is the separation between two slit. So, E is the slit width and D is the slit separation. Now, the plane wavefront is incident normally on this slit, that is a consideration, and a part of that wavefront is passing through S1 and another part will be passing through S2, and this wavefront will be sending the secondary wavefront towards the screen, and the secondary wavefront without any deviation will be moving and focused at a point O. So, obviously the point O will be the point of maxima, and those light deviate, those wavefront deviate by an angle theta will be focusing at point P. Now, if theta changes, the P also changes. So, P is an arbitrary point on screen. So, we have to calculate what is the intensity at point P. Then we can easily have how the intensity distribution due to this double slit diffraction. So, we are assuming here S1 and S2, these are essentially two coherent sources of light, and basically this S1 is a single slit, S2 is another single slit. Now, the diffraction taking place from single slit of S1 and S2, and a resultant amplitude of R0 into sin alpha divided by alpha will be producing due to a single slit S1, and separately we will have the same amplitude by S2. That means each source is sending a wavelet or secondary wavefront of amplitude R0 into sin alpha divided by alpha. When these two wavefronts are meeting at this particular point, then the resultant amplitude at that point will be the result of the interference or superposition between these two wavefront. That is a concept we are going to discuss here. So, to calculate the resultant intensity, first of all we have to have the equation for the path difference and phase difference. We have to have the path difference. Now, we are taking the point as central point of S1 and correspondingly we are taking the central point of S2. So, S1 and S2 these 2 points are 2 equivalent points. If I am considering a point on the top of this S1, I shall consider the top point of S2. These are the 2 equivalent points of this slit S1 and S2. Now, the distance here, this will be E by 2 and this distance will be E by 2. So, the total distance from the center of the slit S1 to center of the slit S2 will be E plus D. In order to calculate the path difference, first of all let me draw a normal to that meeting at point K. Now, from S1 to P the path from S1 to P and from K to P, these are equal, then obviously the path difference between these 2 wavefronts shall be S2K. Therefore, the path difference S2K from this triangle, if this angle is theta, this angle is also will be theta, then S2K the path difference is equal to S1 S2 sin theta. Now, you know the distance S1 S2 is the distance from the center of S1 to center of S2, therefore, that is E plus D sin theta. So, this is the path difference. We know the relation between phase difference and path difference as phase difference is equal to 2 pi by lambda into path difference. Then now we will have the equation as for the phase difference delta 2 pi by lambda into E plus D sin theta. Now, we will calculate we have to derive what is the resultant amplitude at point P, then obviously we can have the equation for the intensity as well. We know that from a single slit, each slit S1 and S2, they are sending a wavefront of with resultant amplitude R0 sin alpha divided by alpha. Now, a wavefront from here and another wavefront from S2, they are meeting at a point P. Now, what shall be the result, what shall be the field, what shall be the equation for the displacement of field at point P due to each slit, that is the value of the displacement of field E1 from S1, I am taking it as E1, then E1 is equal to R0 sin alpha divided by alpha into cos omega t minus alpha. This is essentially the equation for the displacement of the field at a point P due to a single slit. Now, we are considering a second slit S2. Now, from S1 and S2 there is a phase difference. Therefore, the equation for the displacement of the field from slit S2 will be R0 sin alpha by alpha into cos omega t minus alpha minus delta, where delta is the phase difference between the light from wavefront from S1 and S2. Here you see in both case the amplitude is R0 sin alpha divided by alpha. So, these two fields are superposing at a point P. Both fields are meeting at point P and they are superposing. Then the resultant field at point P shall be E1 plus E2, E is equal to E1 plus E2. Now, I can substitute the value of E1 and E2 in this equations. So, we will be getting the resultant field E is equal to, this term is E1 and this term is E2. So, just substituted the value of E1 and E2, that is R0 sin alpha divided by alpha into cos omega t minus alpha, and the second term obviously E2 is there. Then I am taking R0 sin alpha divided by alpha as a common factor, and then we have cos omega t minus alpha and cos omega t minus alpha minus delta in the bracket. Now, this will be cos A plus B form. So, this is cos A and this shall be cos B. So, cos A plus B can be expanded like to cos A plus B by 2 minus into cos A minus B by 2. So, if I am expanding in this way, so we will have the equation for the resultant field as R0 sin alpha divided by alpha. So, 2 into cos A plus B will be giving us cos into 2 omega t minus 2 alpha minus delta all divided by 2, and then cos A minus B by 2 will be giving us cos delta divided by 2. Then here cos delta, delta is the phase difference between, this is a constant term I am taking on the left hand side, then E is equal to 2 R0, this 2 R0 sin alpha divided by alpha cos delta by 2, and this one is the, this one represent the variation of the displacement of field at that particular point. That means this will be giving the equation for the amplitude. For the simplicity, I am just substituting this delta by 2 term as beta. So, the equation we will have for the resultant displacement of field is 2 R0 sin alpha divided by alpha into cos beta cos omega t minus 2 alpha minus beta. This is the resultant equation for the resultant field, and here beta is delta by 2 we have taken, and beta by 2 will be giving us the pi by lambda into E plus d into sin theta, where delta was 2 pi by lambda into E plus d sin theta. So, just dividing by 2 itself, and then the resultant amplitude in this formula will be this one, R is equal, the resultant amplitude, I just let me take it as this entire term as the resultant amplitude R, then we will have the equation for resultant amplitude is R is equal to 2 R0 into sin alpha divided by alpha into cos beta. This can be easily obtained through another method. So, we know that we are considering 2 slit, each slit is sending wavefront of amplitude R0 sin alpha by alpha. Therefore, this can be taken as 2 vector. So, one vector with the amplitude R0 sin alpha divided by alpha and another with the R0 sin alpha divided by alpha. There will be a phase difference of delta in between. Two, delta is a phase difference between 2. So, just here we can use a simple vector addition method, and then obviously we will be getting the resultant amplitude R as like vector addition by using a vector addition, and you can have this formula by simple vector addition formula, that is where resultant amplitude is equal to a square plus b square plus 2ab cos angle delta. So, just substituting the value, first vector square of first vector square of second vector 2 into first vector into second vector into angle cos delta. Simply I am just expanding R0 sin alpha by alpha taken here as a common factor from all, then we can have 2 into 2 cos delta. So, you can simply derive like this, R0 square sin square alpha divided by alpha square into 4 into cos square delta by 2. Therefore, the square of the resultant amplitude R square can be 4 R0 square sin square alpha by alpha square into cos square beta, where beta is the pi by lambda into E plus d sin theta. So, this way you can also calculate the resultant amplitude. Square, here it is the square of the resultant amplitude. If you are taking the square root of this, we will be getting 2 R0 square. If you need, I will just write here. So, R is equal to 2 into R0 sin alpha divided by alpha cos beta. So, this shall be the resultant amplitude. The same result we have obtained in the previous method as well. So, if I am taking the square of that amplitude, then we will have the equation for the resultant intensity. Then therefore, that is the resultant intensity from 2 slit, we will have the equation I is equal to I0 sin alpha by alpha all square into cos square beta. Here in this formula we have 2 terms. One term is I0 into sin alpha by alpha all square. Now, this term gives the intensity distribution in case of diffraction, in case of diffraction from a single slit, and the second term cos square beta, that gives the intensity distribution in case of an interference pattern due to a double slit experiment that we have already been discussed in interference and Young's double slit experiment and all. So, essentially what is the concept here? Eventually the concept here it is, in a double slit experiment, the resultant intensity is the combined effect of resultant intensity formed because of the combined effect of interference phenomena as well as the diffraction phenomena. So, to understand a detail about how the formation of the interference pattern, we have a screenshot of the animation obtained from a GeoGebra. Here it is the intensity distribution due to interference. So, we know that the in the double slit, in case of diffraction from a double slit, the intensity distribution is the combined effect of interference and diffraction. So, here I am showing the interference pattern only. So, in interference pattern we know that there will be alternate dark and bright fringes. That means we will be having alternate maxima and minima. So, this point is the maxima point and this one is the minima point, and the distance between these two fringes or the maximas will be equally spaced in case of an interference pattern, and the maximum intensity for all the maximas, and the value of that intensity for all maximas will be equal in case of interference pattern. This type of fringes or this type of interference pattern, this type of pattern we can observe from an interference, through an interference. In the actual view, in the real view, the interference pattern just look like this. So, this is one fringe, this is another fringe, third fringe, and almost equal intensity we this all have. Now, if we have a diffraction pattern, in the background I am giving the interference pattern as well. In the diffraction pattern, you know that there will be a central maxima. This is with the maximum intensity we took, in our case it as I0, that is the central maxima intensity. Then next we will be getting a minima here, then secondary maxima, then minima, and then another secondary maxima with decreasing intensity. Now, these two interference pattern and diffraction patterns are clubbed together, and a modulated pattern we can observe when we are considering the double slit. And the real view of that diffraction pattern, you see here there is a central maxima, then minima, then secondary maxima, like so on. So, what happen when these two are both clubbed together and modulated? So, we will be obtaining the interference pattern is modulated accordingly to the diffractions. So, this is an interference fringe, and this interference fringe increases, and this is the interference fringes modulated with the single slit diffraction pattern as we have discussed. So, in the real view you can see this is the central maxima because due to the single slit experiment, and this is these are the interference pattern. Now, these both together it is forming a pattern like this. Here you can very clearly see that the central maxima, corresponding to the central maxima, there will be some dark spot like this. So, that corresponds to the interference pattern inside the central maxima. That means you can clearly understand that the pattern formed is the combined effect of the diffraction and interference. If we are considering only the pattern of double slit, it just look like this. So, this will be a maxima center. Well, now this experiment, this diffraction from a double slit obviously leads to a new definition for that diffraction, that is, diffraction is the interference of the secondary waves originated from the Hall wavefront or originated from the different parts of the Hall wavefront. Now, why the term interference here? So, we know that interference is basically the superposition of two or more waves or beams from different sources. But what is the main difference right now when what is the main difference for a diffraction here? Now the diffraction can be defined as the phenomena in which interference take place or superposition take place, in which the resultant amplitude at any point on the screen is obtained by integrating the effect of the large number of infinitesimally small elements from whole wavefront. We can find what is the condition for the formation of maxima and minima. So, from the interference pattern, interference term, we have two terms, one is cos square phi and another one is sin square alpha divided by alpha square. So, here cos square in the interference equation that indicate that gives the interference term, and the maxima obtained when cos square beta is equal to 1. When cos square beta is equal to 1 means the beta shall be plus or minus n pi, where n is equal to 0, 1, 2, 3, 4, etc. Here you may remember the equation for beta is pi by lambda into e plus d sin theta, and that shall be equal to plus or minus n pi here. So, this will be giving the maxima because of the interference. So, this eventually we obtain e plus d sin theta is equal to plus or minus n lambda, where n is equal to 0, 1, 2, 3, 4, etc. So, when n is equal to 0, what happens? When n is equal to 0, the equation here, this term becomes 0, that means e plus d is not a 0 term. So, sin theta shall be 0 and theta shall be 0. So, when theta is equal to 0, then we obtain a central maxima of the interference pattern. That means interference pattern modulated with the central maxima of the single slit diffraction, and we will be getting the maximum intensity at that particular point. Now, how the position of minima? We know that the position of minima, you can take it from the single slit interference pattern itself. So, I is equal to I0 into sin alpha by alpha all square, that is the equation for the resultant intensity from a single slit. Now, for minima I shall be 0, and that means here sin alpha shall be 0 and alpha cannot be 0, because we have discussed already what is the reason in the last lectures. So, that means sin alpha is equal to 0 means alpha is equal to plus or minus m pi. Substituting the value of alpha, pi is sin theta divided by lambda will be giving you and that is equal to plus or minus m pi, and if I am cancelling this pi and pi from here and taking lambda this way, then we can have E sin theta is equal to plus or minus m lambda, that will be giving the position of minima. Here you can see an animation which is made by a GeoGebra software. Here this is the experimental setup, first slit and second slit here, and here we can find the two types of pattern. One is the interference pattern, and the dotted curve here it is the diffraction pattern, and the red line which is the modulated pattern because of the double slit interference. And what happens if lambda changes? You can see this is the let us change the lambda. If lambda changes, how the this pattern changes, you see. So, if the lambda comes to in a green region, so what happens to the width of the central maxima, you can see, and how the interference pattern changes. And let me keep this in somewhat in a orange region itself. Then if I am changing the width, slit width, how the pattern change, you see, the pattern changes like this. I am increasing the pattern. Now, I hope this is, I hope this is visible how the pattern changes. If I am changing the slit width, then the pattern the width of that pattern becomes narrower. If I am decreasing the separation between two slits, what happens? So, the interference fringes becomes apart. Now, I am increasing the slit width, then interference, it does not change the diffraction pattern, you see. If I am increasing the d value, the distance between screen, Now how the change is happening? You see both diffraction pattern and interference pattern changes. Okay. So I hope you understood how this this pattern changing with wavelength, slit width, slit separation, and the separation between source and screen. Considering two patterns, one a diffraction pattern and interference pattern, here you can see few maximas. This is the maxima formed by an interference pattern. At that particular point, a minima of the diffraction pattern is forming. So in this case, certain order of the interference pattern will be missing in the resultant pattern, and this missing maximas or interference maxima, we just called it as missing order in double slitted diffraction pattern. Here there are two conditions. One is the condition for maxima of because of the interference pattern, that is E plus d sin theta is equal to plus or minus n lambda, where n is equal to 0, 1, 2, 3, 4 etc. And the condition for minima from single slit, that is E sin theta is equal to plus or minus m lambda. Now we know that in case of missing order, the maxima for interference and minima because of the diffraction from single slit are simultaneously occurring at the same position. That means these two conditions are simultaneously occurring at a particular angle theta. This is the condition. So in this case, what I am doing, I am just dividing these two. So we will have E plus d sin theta divided by E sin theta. On the left hand side I have divided like this, on the right hand side I have n lambda divided by m lambda. Here I can cancel lambda and lambda, sin theta and sin theta getting cancelled out. Then the formula here it is E plus d divided by E is equal to n by m. So this condition gives us the position of or the order of the missing spectra, or that means if I am here E is the slit width and D is the slit separation. Supposed to be E is equal to D, what happens? The slit width and slit separations are equal. In that particular case, we will have this equation as 2E divided by E is equal to n by m, where this n indicate the diffraction pattern and m indicate the n indicate the interference pattern and m indicating the diffraction pattern, order of the diffraction. So here E and E will be getting cancelled out, so we can have n is equal to 2m. That means if m is equal to 1, 2, 3, 4 etc., then if m is equal to 1, 2, 3 etc., m is equal to 1, 2, 3 etc. So correspondingly the n value is 2 into 1, it is 2, then comma, then 2 into 2, that is 4, then 6 and so on. What it does mean here, if slit width is equal to the slit separation, then the second order will be missing and fourth order will be missing in the interference pattern and sixth order will be missing in the interference pattern. So you can calculate what happens if E is equal to 2D. So you can easily calculate which all order will be missing if the slit width is the double of the slit separation, or in opposite, in any of the case you can find it. To discuss what is the difference between an interference pattern and a diffraction pattern. So let us discuss what are the major differences here. So first point here, interference is the phenomena, it is due to the superposition of light wave coming from two coherent sources, two separate coherent sources. However, in case of diffraction, it is the phenomena due to the interference or superposition of the secondary wavelets coming from the different part of the same wavefront. The second point, the fringes may or may not be the same width in case of a diffraction, in case of an interference pattern, And in case of diffraction, the fringes are never of the same width, and you know that the width of the central maxima will be large, and obviously the width of the secondary maximas will be smaller in comparison with the central maxima in case of diffraction. And in case of interference, all the bright fringes are of the same intensity, and in case of the intensity in comparison with the central maxima, the intensity of the secondary minima will be very small, and that means the intensity of the successive bright goes on decreasing. And the intensity in case of interference, the intensity at minima is usually be 0 or very small. We can easily have a contrast difference between the bright and dark fringes. However, in case of diffraction, we may not have that contrast. We cannot have a good contrast between bright and dark. That means the intensity of the minima may not be 0, and there will be a poor contrast between the bright and dark fringes in this case. With this, I am ending today's session here, and we have discussed the Fraunhoffer diffraction at double slit. We have discussed what is the intensity distribution, we have derived what is the equation for the intensity, and then we have discussed what is the condition for the how the modulation take place between the two different patterns of interference pattern and diffraction pattern, and we have discussed what is the missing order in case of a double slit diffraction. I hope you could follow me in this session. With this, I am ending here. Thank you.